This is a chapter 9, question 14. So chapter 9, question 14 from the Graviter and Molyneux textbook. So this is a single samples t-test. Many animals, including humans, tend to avoid direct eye contact and even patterns that look like eyes. Some insects, including moths, have evolved eye spot patterns on their wings to help ward off predators. Shelfay in 1976 reports a study examining how eye spot patterns affect the behavior of birds. In the study, birds were tested in a box with 2 chambers and were free to move from one chamber to another. In one chamber, 2 large eye spots were painted on one wall. The other chamber had plain walls. The researcher recorded the amount of time each bird spent in the plain chamber during a 60-minute session. Suppose the study produced a mean of, so M, mean of M equals 34.5 minutes on the plain chamber, with a sum of squares of 210 for a sample of N equals 15 birds. Note, if the eye spots have no effect, then the birds should spend an average of mu equals 30 minutes in each chamber. Is this sample sufficient to conclude that the eye spots have a significant influence on the bird's behavior? Use a two-tailed test with an alpha of 0.05. Then we will compute estimated Cohen's d to measure the size of the treatment effect. The first thing, the full 4-step hypothesis testing procedure. The first thing we are going to do is step 1. We're going to do the hypotheses. The hypotheses. We've got a two-tailed test, our null and our alternative, or our alternate. The null is that the mean of the group is equal to 30. That the eye spots, this is the idea here, is the eye spots have no effect on behavior. The animals spend the same amount of time in the chamber with eyes as the chamber without eyes. And here, what we're testing is that the mean, do the birds spend longer in the chamber with eyes or in the other? So if the null is that they're equal, the alternative is they're not equal. If we look at the prior research, there's probably reason to believe that they would spend more time in the room without eye spots, but this is asked for a two-tailed test, so these are the hypotheses that we want. Step 2. Find our critical values. In order to find the critical values, we need to have a two-tailed test. We know that. We have an alpha of 0.05. We know that. We need our degrees of freedom, which is n-1. We have 15 birds. So 15 minus 1, our degrees of freedom is 14. Now we're going to go to table B2, and we're going to look up what our critical value is. We're going to go plus or minus on this one because it's a two-tailed test. So here I am on the statistical tables, Table B2, the t-distribution. I have a two-tailed test, so I want to look at proportion in two tails combined. And I have an alpha of 0.05, so proportion in two tails combined, 0.05. This is the column, the column that I want to look at. I'm going to go down until over here I get to 14. So I'm going down in this column until I get to that degrees of freedom that I just calculated. My critical values are going to be plus or minus 2.145. So if I look at how that's going to look in terms of drawing it out, because I do recommend that you draw it out. It's plus or minus because it is a two-tailed test. So we have these two boundaries. Over here, negative 2.145. Over here, positive 2.145. And then we will use this in step 4. If we calculate in step 3 a number that falls in this area, we're going to fail to reject the null. If we calculate a value out here in the critical regions, we are going to reject the null hypothesis and accept the alternate hypothesis. So our critical values plus or minus 2.145. And we have that plus or minus because it's a two-tailed test. For step 3, we're going to calculate the test statistic. In this case, a single sample t-test. Before we jump into that, we need to calculate our estimated standard error. Before we can calculate our estimated standard error, we have to calculate either our standard deviation or our variance, because the question gave us sum of squares, and the formula for the estimated standard error uses either a standard deviation or a variance. It doesn't use sum of squares. So in step 3, our first is we're going to go with variance. Y square root something only to square it later, etc. Right? So here, sum of squares divided by n minus 1. Now note, when we calculated our degrees of freedom was n minus 1, which was 15 minus 1, which was 14. This isn't coincidental. There is the degrees of freedom here is why our degrees of freedom in our t-test is what it is. So here we've got 210 divided by 15, subtract 1 is 14. Which is 15. So our variance is 15. Now we can calculate our estimated standard error. We can put our variance, divide by the number of scores, and take the square root of the whole thing. So 15 divided by 15, because that was our sample size, right? So we calculated our variance as 15, but our sample size was also 15. And then we'll take the whole square root. So 15 divided by 15 is 1, and you take this, so let's write this out. So it's the square root of 1. The square root of 1 is 1. Now that we have our estimated standard error, we can calculate our t. The t value for a single sample t-test is m, subtract the population value divided by your estimated standard error. The mean of Sorry, my computer's doing funny business. The mean of the sample is 34.5. The mean of the population was expected to be 30, divided by the estimated standard error, which was 1. So we've got 4.5 divided by 1, which is 4.5. I'm showing all of these steps, even though it's divided by 1. I could have skipped to just this. It's useful to show all of your work in each of your steps, because if something goes wrong, showing more of your steps in your work allows me to give you more part marks. When I grade exams, I'm always actively looking for ways to assign part marks. So the T that we obtained is 4.5. So T obtained. I'm just writing it down here because I'm going to erase all this, and I have, I don't trust my mouth on this. Let's go with that. So, step 4, we need to make a decision, interpret it, give me evidence. So let's draw it out and see how these numbers fall. The critical values were minus 2.145 and positive 2.145. The value we just obtained was 4.5. It's outward, right? It's beyond this score. It's bigger than this score. It falls in this critical region. So we are going to reject the null and accept the alternate. That's your decision. This can serve as your evidence, and you need to interpret that. There's a significant difference. If you reject the null, you're saying there's a significant difference. If you fail to reject the null, no significant difference. Not an insignificant difference. It's still meaningful, potentially. It's just not significant. So within the context of this question, then we would say that the birds spent significantly more, because that's the number that we were testing. It's more. T is positive. Birds spent significantly more time in the chamber without eye spots than they did in the chamber with eye spots. So there's a significant difference. And that's important to me to see that you know what is what. So I'm going to pause here, and then we will resume looking at the effect size measure that is asked in part B of this question.